Second, I'll publish site to the stream. I need to publish a link for the stream. Otherwise, no one can connect us. This one, okay, and. Okay, let's go. It's time. It's time to start. I don't need this one. Okay. Our previous subject of interest was system bits return. Let's say we have transfer of some, let's say, direct and circuit of return with its transfer function beta. So we have the direct K and return beta. Overall transfer function, if this, say, okay, we can write Sx as a function of frequency, Sy as a function of frequency, Sy was okay, no frequency divided by 1 minus okay, no frequency beta as a function of frequency. We can switch to Laplacian space. So if we perform Laplacian transform on Sx, being function of time, we will get, let's say, Sx as a function of complex frequency being dot omega. Laplacian transform on Si gives us its image in a complex space, in a space of complex frequency. For our system in Laplacian space, transfer being or one okay, we can maybe to make it a bit clear. We can write 1 minus E beta as a function of complex frequency. Or one against A 0 A 1 plus A N. Here are rules, all these are rules of characteristic equation. If our system can be described as A0, let's say n time plus A and x equals to 0, if our system can be described as a differential equation, solving this equation yields us a roots. So a characteristic equation. In idea, we need to solve an equation A0 minus 1p, it's plus equals to 0, so-called characteristic equation. We will get a sum of roots. These roots are corresponding to the poles of transfer function. We can use, we can take transfer function, take an absolute value at some frequencies. We will have coordinate system like something like this, and we will see at some frequency pulse where transfer function goes infinite. I'm not the best. It's something like, oh, that's it. Here goes to infinity. It's an absolute value of transfer function. And coordinate system, C, J omega, here I have one pole. System will oscillate at frequency. This pole corresponds to some frequency. It's a point where system will oscillate, own frequency. System is stable if all roots, say I have this coordinate system. As I draw, if I have 0 here, I need to firstly remove it. Alright, if I have something like this, to infinity, system will be stable. If I have a real part of all roots from 1 to less than 0, it's like this system. It can oscillate. It can oscillate, but it will return to the stable condition. If I have root here, it's like this. It's an unstable system. It will fail. At this moment, if you pay attention, I used transfer of the open loop system. Now I want to switch to the closed system. What will be the effect of return? This one is characterized with equation. If real part of all root is on the left side, I can frequent J omega constant. If all roots are here, system is stable. If one single root is on the right side, not stable. Now question, how return will influence it? This one. To test it, I'll use a very simple system. I have an electron valve, coil capacitor, and a resonant contact with contact inductance and contact capacitance. I can change it. Linear system loaded with resonant circuit. I will add resistance to, it was loss in contact and resistance of load. This, I have this load here. Not important. Important thing. I have another small coil. Oh, the yellow one, the big one. This coil. This capacitance both is contact capacitance, and I have this small coil. I can move it on my wheel. I can adjust coupling, coupling between main contact and the input of my linear system. I have something like this. Linear contact, input, and adjustable return. By changing the distance and orientation of coil, I can change coupling between output and input. That's how I can control feedback and analyze effect of it. Easy. Okay, come close. So here is my setup. The contour coil with this capacitor and the small one, this one. I can put it in any position, and this way I can change coupling between output and input and control the feedback. Let it be A point. I'll need it. My valve have a characteristic something like this. Anode current as a function of grid voltage. At this point, delta gauge, delta of anode current, amplification parameter being it's, can we say, sensitiveness of linear our linear stage. Transfer coefficient can be written approximately as S minus, because we have an inverting amplifier. Increase of anode current means decrease of output voltage. That's why minus sign. From frequency. Approximately, this factor multiplied by load impedance, its impedance A0 between the A point and Earth. The series capacitor is taken much higher. This one is set for half of nanofarad, and series capacitor 10 nanofarad, something like this. It's 10 times higher, so it's not playing a significant role. Bad feedback can be, it's exactly plus minus coupling multiplied by content inductance. I can write S contour resistance 1 plus contour capacitance omega plus 1 against dot omega contour inductance and again contour resistance. I'll get image of it simply replacing omega with complex frequency pair. Again, it's a frequency, complex frequency of Laplacian space. So image of the A will be resistance 1 plus resistance plus 1 against P would be preferable to write it in a bit different way. S A E divided by contour capacitance P square plus 1 against R. It would be P, okay. And plus 1 against L. Or this one looks very familiar. P divided by contour capacitance P square plus 2 alpha plus omega 0 square. Here, omega 0 is a contour resonance frequency. If we write down imaginary part of 1 against the input conductance, or better be input admittance equals to 0, we will have current resonance condition, leading us to resonance frequency 1 against square. It's omega. Alpha is an oscillation decrement. If you have decaying oscillation, alpha determines this line, it's a decrement. Now we can write down overall transfer function. Our system will have transfer function 1 or B divided by B squared plus 2 alpha P plus omega 0 squared multiplied by 1 plus beta divided by P and divided by P squared plus 2 alpha P plus omega 0 squared. Here it is, overall transfer function. One second, I will write it in more usable way. What do you want? Oh, didn't find any problem. Okay, let's make it clear. So it will be I need a minus sign here. Multiplied by frequency divided by contour capacitance frequency plus omega 0 squared. here alpha decrement is 1 divided by double contour resistance, contour capacitance, and omega 0 against 1 L. It's a contour resonance frequency. One note. When we are at the frequency of resonance, transfer omega 0 will be minus L contour. It's negative. It's less than 0. This means, what if we need bad negative, if we need the negative return, we should have a positive sign of mutual coupling to compensate inversion. If we need beta greater than 0, we need to have an inversion, negative we need negative coupling. Okay, let's see at first case of negative return. So let's put bet M with the plus sign. That means what overall feedback will be negative. We'll see overall transfer being is divided by contour capacitance multiplied by P divided P squared plus double alpha plus ms omega 0 square P. I need to continue plus omega 0 square. Now we need to analyze this overall system. How? Take the divider and solve an equation when it's equal to 0. You need roots of divider. And what will we have? We will have two roots equals to minus alpha plus ms omega 0 squared divided by plus minus plus minus j square root of omega 0 square minus alpha plus ms omega 0 square divided by 2. What do we see? We have two roots, two own frequencies. They are conjugated. So actually it's one own frequency. Because roots are conjugated, we will have one frequency. But we have a minus sign here. That means what real part of all roots is less than 0. And system should be stable in any case. Let's check. Let's see our system. I'll use a simple way to test our system. What we got? Amplifier, contour, mutual coupling, I will attach a battery to the input. Small resistance here. It's like striking with a hammer. I want to repeat old school trick. Strike with the hammer. Turning fork is an oscillation system. And in a row of hammer will be this battery. We can see it oscillates. Not oscillates. I'll use this battery as a hammer. Touch. Small. Small battery. This. This one is okay. And I need also this one. second. I'll use another switch. This one goes and this one. Goes here. Oh, this one is better. You can see how contacts. Oh. Contacts are not interrupted instantly. It's some vibration. You see the connection. Oh, this one. Nice. Take a switch away. What we got here? Decaying oscillation. One more. And I'll switch. Here is one coil, another. Coupling is weak. Now system have no return. Here is process after I hit with the hammer. I start with the hammer, but say I have added battery voltage to the coil and then brought discontinued the current. And we have these decaying oscillations. I will put it into memory. 1 second, save recall. No. Save value for channel 1 to reference. Yeah. The white line is a process without coupling. Now coils are closer. Look it there. Coils are closer, coupling is stronger. I have introduced negative return. No, this one is not the best. Like so. We can see it's decayed a bit faster. Now, let's put our coils. Close to one another. I have increased negative coupling. You see the effect? Oscillations decay much faster. Negative return makes system more stable and more linear. How can I, okay, it's brutality. Yeah. I have put them as close as possible to make coupling as strong as possible. We saw effect of strong coupling. Now, not a good shot. Okay. On. Okay, it is fast decay. For comparison, average coupling. Okay. Let's say average coupling. This one is. And the strong one. The stronger coupling between coils, the faster process comes to a steel. The system becomes more stable. It's like I had a system like this with the ball. I can push the ball up and it will return to the stable. And when I added a negative return, it's like putting a magnet below. It makes system more stable. We can see again. Weak coupling, strong coupling. And now, all this with negative return. So any negative return makes system more stable. And what about positive? One second. I'll switch the coil polarity. Now, coupling will be positive. Now I will switch back to pink mines. Now coupling will be positive. I will have again two roots, minus alpha minus m omega 0 squared divided by plus minus square root y square root omega 0 square minus alpha minus omega 0 and divided by 2. And here I need square. Yeah. We need to take a look on the real part. Here it is, the real part. We got two cases here. Until alpha minus omega 0 square is greater than 0, or resistance is smaller, system will remain stable. Let's take a look. Oh, again, system. Since if we have a real part, system will remain stable until I minus m omega 0 divided by 2 is greater than 0. I'm repeating for record. So let's take a look. Weak connection. We can see system is stable. I'm coming closer. Approximately the same. Coming closer. Once again. Maybe I need to. I can change scale. here make another record. To make it more visible. Save channel 1. I saved process with this coupling to change the time scale. Now stronger coupling. We can see process lasts longer, much longer. Closer. Don't. It's stable, but you can see how long it takes. How long it takes to stabilize. Now I'm on the edge. Here. I'm on the edge. Hey. Whoa. See, I'm on the edge of stability. System started to oscillate. Please. Oh, decaying, system still stable. Bit stronger. Still stable. 1 more millimeter. Stable. Still stable. System not stable. You see oscillation. Continuous. Now I can. Ooh. Now system is not stable. It's oscillating. If I have a limiter here, this neon works as a limiter. In theory, without limiter, system will break, like the Tacoma-Narrows bridge. Now it's in resonance regime. It's oscillating free. Smaller coupling, silence. System stable. Big, stronger coupling, and it now oscillates. Now it's become a generator. Since I have a resonance contour here, it become a generator of harmonic signal. its reference. Now it's generated. By changing capacitance, I can change oscillation frequency. So at a small coupling, system remains stable. Still stable. Yes, it now generates. Stable. It's now it's become a generator. It's a stable. Without limiting, in theory, voltage can go up infinity. But I have a limiter here. Snell valve. Anyway, valve, since it has saturation, it will limit the amplitude of oscillation. But in theory, without limiting factor, system will break. What can we conclude? If we have a negative coupling system, more stable, or negative feedback. System with negative feedback is more stable compared to system with no feedback. System with positive feedback at a low, let's say, at low feedback, so low couplings, remain stable, but they always the border below that system is no longer stable. It begins to oscillate. Begins to oscillate. Or becomes, and in my case, it becomes a generator. With a strong coupling, we can see distortions. Big coupling, nice. Nicely generates harmonic signal. If we wanted harmonic source, okay, but for control system, for example, it's a disaster. It will go up, let's see, one direction, up, open, till opens fully, and then go down fastly, till finally close. Meaning hydraulic shock, or possible, I saw a gas pressure system, which oscillating up, down, and valve broken. Yes, you need another high pressure valve, quite expensive. Because system wasn't stable. Problem was, when we need to, let's say for example, we need to keep voltage constant, voltage stabilized. If load voltage decrease, we need to amplify. It's a positive coupling. Positive. So voltage stabilized with potential unstable. We need to take measure for preventing it, to prevent it from oscillation. Stable, unstable. analog generator. 5 volts, 3 volts output. It's divided. It's now we can reach some 300 volts here. I don't want experiment. Running it without load and without limiter. Yeah. Nice generator. Sometimes it can be used for fun. Where is my tool? Resonant transformer. The idea Catode source. Was 250 volts. One coil with coupled. This coil, this large coil, and white capacitor, this resonance contour. Smaller coil below takes a signal. It's a return coil. And another coupled coil, this longer one. What do I need? Altogether, it's a resonance transformer. With this ferrite rod, I'm changing inductance of the secondary coil to turn it in. I need to turn this contour, this ring and this coil to the frequency of the main contour of this smaller coil and this capacitor. A small piece of dark energy. It's a dark energy. It's absolutely clear. I got no batteries here. Can be noted 2 points of resonance. They are well coupled, so characteristic has 2 points, 2 maximums. той. Resonant transformer. Again, it's the same thing. Auto-generator. Resonance contact at the output, and with this coil, signal is taken to the amplifier input. This small valve acts as a linear stage. I got current resonance here, and secondary winding with capacitor adjusted to be in resonance with the primary one. Nice toy. Только в нем. Neon discharge one. Funny thing. So, what's the conclusion can we make? System with return, or system with feedback, if feedback is negative, becomes more stable when the system, comparing to system with no feedback. If system has a positive return, it may remain stable, but there always is some point when system will lose its stability. And will begin oscillate. With possible devastating effect. Possible system will destroy itself. with this experiment, I would like to show another one. Another one. This is not needed. I would like to show another one. It's for the next, I think, this one is not needed. Another one, it's effect of mutual effects of two signals. What about time? I can assemble network now. Today we have another one scheduled at 4 or at 12.
At 12, I think.
12.
Just after this.
Just after. Okay. Okay, I'll start assembling the network, but I think I need another string for it. Separate. I will end this one. No one here. I will start another. Stream to show pair of interesting effects.
So that's why when you have op-amps, a lot of circuits require for you to have negative return to negative.
Okay, it demands what you want to get. But yes, if you want to have an amplifier, stable amplifier, you always think, I need a negative return. I need to make it more stable. Or amplifier may become a generator.